Welcome! In this session, we will tackle the problem number 767, Reorganize string. Together, we'll explore how to approach this intriguing challenge, step by step. Let's dive in and uncover the solution. In this problem, we are tasked with rearranging the characters of a given string S such that no two adjacent characters are the same. If it is impossible to achieve this, we should return an empty string. The input is a string S that consists only of lowercase English letters, and its length is guaranteed to be between 1 and 500. The output will be either a rearranged version of S meeting the condition or an empty string if the condition cannot be satisfied. For example, if the input string is S equals OB, a valid output would be ABA because the characters are rearranged such that no two adjacent characters are the same. Looking at another example, if the input string is S equals OB, the output should be an empty string. This is because there is no possible way to rearrange the characters such that no two adjacent characters are the same. On the other hand, for S equals velvlo, we can find a valid arrangement like volvav, where no two adjacent characters are identical. This demonstrates that the solution may involve finding one of several possible valid arrangements, depending on the input string. Furthermore, the problem provides some constraints and edge cases to consider. The length of the string S is between 1 and 500, and it contains only lowercase English letters. For edge cases, if the input is a single character like A, the output is simply A because there are no adjacent pairs to worry about. If all characters are the same, such as AAAA, the output must be an empty string since rearrangement is impossible. For highly imbalanced frequencies, like OB, a valid output could be OBOBA, where the condition is satisfied. And if the input string is already valid, like ABAB, no rearrangement is needed, and the output remains the same. These examples highlight the variety of scenarios the solution must handle. To solve the problem of reorganizing a string such that no two adjacent characters are the same, several approaches were considered. One of the most straightforward ideas is the brute force approach, which involves generating all possible permutations of the string and checking each one to see if it satisfies the condition. While this might work for very small strings, it is computationally infeasible for larger inputs. The reason is that generating permutations has a factorial time complexity, O(n), which grows extremely fast as the length of the string increases. Additionally, the process of checking each permutation for adjacency violations adds further computational overhead. Due to these inefficiencies, the brute force approach is not a practical solution. A more promising idea is to use a greedy strategy with a max heap. The insight here is that the most frequent characters in the string are the ones most likely to cause adjacency conflicts. By leveraging a max heap, we can repeatedly select the most frequent characters and interleave them in a way that avoids placing the same characters next to each other. This approach is much more efficient and directly addresses the problem's constraints. The greedy approach using a max heap involves several clear steps. First, we count the frequency of each character in the string using a hash map. This helps us identify which characters are most frequent. Next, we add all the characters and their frequencies into a max heap, which allows us to dynamically retrieve the character with the highest frequency at any given time. Once the heap is initialized, we repeatedly extract the two most frequent characters. The first character is placed in the current position, and if the second character is available, it is placed immediately after. After each placement, we reduce the frequencies of these characters and push them back into the heap if they still have remaining counts. A critical condition to check during this process is whether any character's frequency exceeds n+1//2. If it does, it becomes impossible to distribute this character without violating the adjacency rule, and we return an empty string. Finally, the result string is constructed by interleaving the characters as described. The complexity of this approach is dominated by the heap operations, with both building and processing the heap having a time complexity of O(n) log n. This makes it a highly efficient solution for the problem. An alternative to the max heap approach is another greedy strategy that avoids using a heap altogether. Instead, we can sort the characters by their frequencies and use a two-pass method to interleave them. The idea here is to first place the most frequent characters at even indices, such as 0, 2, 4, and so on. Once the even indices are filled, the remaining characters are placed at the odd indices, like 1, 3, 5, and so forth. This approach still begins by counting the frequency of each character. After sorting the characters by frequency, the even indices are populated first to maximize the distance between identical characters. Then, any leftover characters are placed in the odd indices. However, as with the heap-based method, we must check if any character's frequency exceeds n+1/2. If that condition is true, we return an empty string because a valid arrangement would be impossible. While this method has a similar time complexity of n log n, due to the sorting step, it requires more manual handling of indices, which can make the implementation slightly more cumbersome. Nonetheless, it provides an alternative way to solve the problem efficiently. Among the approaches considered, the greedy strategy using a max heap was chosen as the optimal solution. This method stands out for its simplicity, efficiency, and practicality in real-time scenarios. The use of a priority queue ensures that we can dynamically manage the most frequent characters and interleave them in an optimal way. While the alternative greedy approach without a heap is also efficient, it requires more manual handling of indices, which makes it less intuitive and slightly harder to implement. On the other hand, the brute force approach, with its factorial time complexity, is clearly infeasible for larger inputs and not a viable solution. In terms of trade-offs, the max heap approach does use additional space for the heap, but this is a small price to pay for its clarity and dynamic character management. Overall, the heap-based approach strikes the right balance between efficiency and ease of implementation, making it the best choice for solving the reorganized string problem effectively. To tackle this problem, we need to rearrange the characters of a string such that no two adjacent characters are the same. If it's not possible to achieve this, we simply return an empty string. To solve this, we use a greedy approach along with a max heap, or priority queue, to ensure that characters with the highest frequencies are placed first while avoiding consecutive placements of the same character. The first step involves counting character frequencies using a dictionary or the collection's counter class. For example, if the input string is ape, the frequency count would result in a dictionary like a2, b2, c2. This gives us a clear picture of how many times each character appears. Next, we build a max heap to manage these frequencies effectively. Since Python only supports min heaps, we can simulate a max heap by storing negative frequencies, ensuring that the character with the highest frequency is always retrieved first. After building the max heap, we initialize two things: an empty list to construct the result string and two variables to track the previously used character and its remaining frequency. Initially, these are set to none and 0, respectively. The core of the algorithm lies in constructing the output string. While the heap is not empty, we repeatedly pop the character with the highest frequency from the heap. This ensures that we are always placing the most available character into the result string. Once a character is added to the result, its frequency is decrement. If the previously used character still has a remaining frequency greater than 0, it is pushed back into the heap to ensure it can be used later. This process carefully alternates characters to avoid consecutive duplicates. For example, if A is chosen, it won't be reinserted until after another character, like B, is placed. At this point, we update the previously used character and its frequency to reflect the character that was just placed. This ensures that the algorithm continues to avoid consecutive duplicates. Once the heap is empty, we check if the length of the result string matches the input string. If they match, it means we successfully rearranged the characters, so we return the result string. However, if they don't match, it indicates that no valid arrangement was possible, and we return an empty string. The algorithm's success relies heavily on the choice of using a max heap. By always selecting the character with the highest frequency, we maximize the chances of spreading out characters that appear frequently. Additionally, the use of prev_char and prev_frequency ensures that no character is used consecutively, maintaining the validity of the arrangement. This approach also accounts for edge cases, such as when a character's frequency exceeds half the length of the string, making rearrangement impossible. The data structures we use play a crucial role in the efficiency of this solution. The max heap, or priority queue, allows us to retrieve and manage characters by their frequencies efficiently, with insertion and extraction operations taking O log n time. The dictionary for counting frequencies provides a quick way to determine how many times each character appears, which is achieved in O n time. When analyzing complexity, the overall time complexity of the algorithm is O, n log k, where n is the length of the string and k is the number of unique characters. This is because we count frequencies in O, n, time and perform heap operations in O, n log k. The space complexity is determined by the storage requirements for the frequency dictionary, the heap, and the result string, giving us an overall space complexity of O, n plus k. These efficiencies make the algorithm well-suited for handling strings of varying lengths and compositions. To illustrate how this algorithm works, let's walk through an example input, s equals ABC. First, we count the character frequencies, resulting in a 2, b, 2, c, 2. Next, we initialize the max heap with these frequencies, which gives us a heap structured as -2, a -2, b, -2, c. Now, we begin constructing the result string. The character with the highest frequency, a, is popped from the heap and added to the result. Then, b is popped and added next. After placing b, the previous character a is pushed back into the heap with its updated frequency. This process continues, alternating between characters and ensuring that no two adjacent characters are the same. By carefully managing the heap and tracking previously used characters, we maintain a valid arrangement throughout the process. The construction of the result string continues until the heap is empty. For the input s equals ABC, the algorithm produces the output string ABCAP. This output meets the condition that no two adjacent characters are the same. If a valid arrangement is found, the algorithm returns this rearranged string. Otherwise, if no such arrangement is possible due to constraints like a character's frequency exceeding the allowable limit, it returns an empty string. This ensures that the solution is both correct and efficient, handling edge cases and complex scenarios seamlessly. To solve the problem of reorganizing a string so that no two adjacent characters are the same, we start by counting the frequency of each character in the string using the counter class from the collections module. This gives us a count of how many times each character appears. Next, we use a max heap to efficiently access the character with the highest frequency. Since Python only has a min-heap implementation, we simulate a max heap by pushing negative frequencies into the heap using the heap.heapPush method. For every character and its frequency in the char_count dictionary, we insert a tuple consisting of the negative frequency and the character into the heap. Once the heap is built, we move on to reorganizing the string. We do this by repeatedly popping the character with the highest frequency from the heap using heap.heapPop. This ensures that we always deal with the most frequent character first. The character is then appended to the result list. Additionally, if there's a previously held character from the prior iteration, we push it back into the heap as long as its frequency is still less than 0, meaning it still has occurrences left to be placed in the result string. After processing the current character, we update the prev_frequency and prev_char variables to keep track of the character we just used and its updated frequency. The frequency is incremented by 1 since we are working with negative values to simulate a max heap, and this adjustment reflects that one occurrence of the character has been used. We continue this process until the heap is empty, meaning all characters have been placed in the result list. Once the reorganization is complete, we perform a final check to ensure the result string has the same length as the input string s. If not, it means the string could not be reorganized to satisfy the condition of no adjacent identical characters, so we return an empty string. Otherwise, we join the characters in the result list to form the final reorganized string and return it. This ensures that the solution either produces a valid output or correctly indicates that no solution is possible. Here, we start by importing the necessary libraries and defining our solution class with the reorganize string method. The first step in the method is to count the frequency of each character in the input string. We do this using a hash map, where each character serves as a key, and its frequency is the value. By iterating through the string with a for each loop, we populate the map, incrementing the count for each character. Next, we use these frequencies to build a max heap, which is implemented using a priority queue. The max heap ensures that characters with higher frequencies are processed first. We achieve this by specifying a custom comparator that sorts based on the frequency values in the map. After adding all the characters from the map to the heap, we move on to the string reorganization process. To build the result string, we use a string builder and maintain two variables, prevchar and prevcount. These help us track the last used character and its remaining count, ensuring that no two adjacent characters in the result string are the same. Now, inside the while loop, we continue reorganizing the string as long as the max heap is not empty. We start by polling the character with the highest frequency from the heap and appending it to the result string. If there are still remaining occurrences of the previously used character, we re-add it to the heap to continue the process. Then, we update our prevchar and prevcount variables to reflect the current character and its remaining frequency, decrementing the count in the hash map accordingly. Once the loop completes, we move to the final step, which is a validation check. If the length of the result string does not match the input string's length, it indicates that reorganization was not possible, so we return an empty string. Otherwise, we return the successfully reorganized string as the output. To solve this problem, we start by analyzing the input string ob. The first step is to count the frequency of each character using Python's counter class. This gives us a dictionary where A appears 2 times and B appears once. Next, we need to prioritize the characters with higher frequencies, so we use a max heap. Since Python's heap module only provides a min heap, we simulate a max heap by pushing the negative frequencies. For this example, we push -2 A and -1 B into the heap. Once inserted, the heap automatically arranges itself to prioritize the character with the highest occurrence, so we have max_heap equals -2 A -1 B at this stage. Now, we reorganize the string by repeatedly taking characters from the max heap. We initialize an empty list result to store the output, along with 2 variables prev_frequency and prev_char to track the previous character and its frequency. In the first iteration, we pop the most frequent character, which is A, with a frequency of -2. We append it to the result and update prev_frequency to -1 and prev_char to A. In the second iteration, we pop B from the heap and append it to the result. At this point, we need to reinsert A back into the heap with its updated frequency of -1. In the third iteration, we pop A again and append it to the result. At the end of these operations, the heap is empty, and the result list contains A, B, A, which is a valid reorganization of the input string. The length of the output matches the input, so we conclude the reorganization is successful, and the result is ABA. For the next example, the input string is OB. The character frequencies are calculated as A, 3, B, 1. We then construct the max heap by pushing -3 A and -1 B into it. The heap prioritizes it due to its higher frequency. To reorganize the string, we initialize result, prev_frequency, and prev_char. In the first iteration, A is popped from the heap, appended to the result, and its frequency is updated to -2. In the second iteration, we pop B, appended to the result, and reinsert it with its updated frequency of -2. This ensures characters are spaced apart. In the third iteration, A is popped again and appended to the result. At this point, the heap is empty, but the reorganization is incomplete. Here, while the heap is empty, the prev_frequency for it is still -1, meaning we cannot include it again without violating the condition of the reorganization. As a result, it becomes impossible to generate a valid output string where no 2 adjacent characters are the same. Therefore, the function returns an empty string to indicate that the reorganization is not feasible. Moving on to another example, consider the input velvlo. We calculate the character frequencies as V3, L1, O1. These frequencies are then pushed into the max heap, resulting in max_heap equals -3 V -1 L -1 O, with V being the most frequent character. To reorganize the string, we repeat the process of selecting the most frequent character from the heap and ensuring characters are spaced apart. In the first iteration, V is popped, appended to the result, and its frequency is updated to -2. In the second iteration, L is popped, appended to the result, and V is reinserted with its updated frequency of -2. This process continues, alternating between characters while maintaining the frequency constraints. By the end, the heap is exhausted, and the result is V, L, V, O, V, which is a valid reorganization. The final output string is vulvav, and it satisfies the condition that no 2 adjacent characters are the same. This demonstrates a successful reorganization for the input string velvlo. To analyze the time complexity of the algorithm, we begin by breaking it down into individual steps. First, counting the frequency of each character in the string is achieved using the counter class from Python's collections module. This involves iterating through the string once, so the operation takes n time, where n is the length of the input string. Next, we build the max heap to prioritize the most frequent characters. Here, we iterate through the character frequency pairs and insert each one into the heap using the heap.heapPush function. If there are k unique characters, this step involves k insertions, each taking log k time. However, since the total number of unique characters, k, is at most 26 for lowercase English letters, the worst-case complexity simplifies to 1. In general cases, where k could vary up to n, this step has a complexity of k asterisk log k. Now, in the step where we reorganize the string, the algorithm processes all characters until the heap is empty. This involves repeatedly performing a heap.heapPop operation to retrieve the most frequent character, which takes log k time. If necessary, the character may also be reinserted into the heap using heap.heapPush, another log k operation. Since we process all n characters in the string, this step takes n asterisk log k time. Finally, the algorithm performs a simple length comparison at the end to ensure the reorganized string meets the requirements. This comparison is a constant time operation, 1. Combining these steps, the overall time complexity includes n for frequency counting, k asterisk log k for heap construction, and n asterisk log k for reorganization. In the general case, where k is less than or equal to n, the total time complexity simplifies to n asterisk log en. For scenarios with a fixed alphabet size like lowercase letters, log k becomes a constant, reducing the complexity further to n. Turning to the space complexity, we start by considering the counter object used to store character frequencies. This requires space proportional to the number of unique characters, k, so the space complexity is k. Next, the max heap stores up to k elements, each representing a character and its frequency, which also requires k space. Additionally, the algorithm uses a result list to build the reorganized string. In the worst case, the list stores all n characters of the input string, contributing n to the space complexity. Temporary variables such as prev_frequency and prev_char use constant space, 1. Adding these components together, the total space complexity is k for the frequency counter, k for the heap, and n for the result list. Since k is less than or equal to n, the overall space complexity is n in the worst case. Now, considering best, average, and worst case scenarios, the best case occurs when the input string already allows easy reorganization, such that no two adjacent characters are the same. Here, the heap operations are minimal, and the algorithm runs in n. In the average case, the frequencies are more balanced, but reorganization is still required. This results in n asterisk log k operations, where k is the number of unique characters. Finally, in the worst case, one character might dominate the input, making reorganization challenging. Even then, the algorithm runs in n asterisk log n, and either produces a valid result or determines that reorganization is impossible. When comparing this approach to a brute force solution, we see a significant improvement in efficiency. A naive method would generate all possible permutations of the input string and check each one to ensure no two adjacent characters are the same. This approach has a factorial time complexity of n, which quickly becomes infeasible for larger inputs. In contrast, the heap-based approach used in this solution optimizes the process by selecting the most frequent characters first and ensuring they are placed at valid positions. This reduces the complexity to n asterisk log n, making it a practical and optimal choice for solving the problem. To summarize the proof of the algorithm's big O complexity, the frequency counting step iterates through the string once, giving a time complexity of n. The heap operations involve insertion and removal, each taking log k, and these are performed n times in total, resulting in n asterisk log k. Ignoring constant factors and lower order terms, the total complexity simplifies to n asterisk log n in the general case. This makes the algorithm scalable for large input sizes, especially when compared to inefficient approaches like brute force permutations. When solving this problem, there are common mistakes that can trip you up if you're not careful. One frequent error is failing to account for duplicate characters in the input string. For example, if you treat the string ob as though it contains 3 unique characters, you'll overestimate the number of possible permutations, leading to incorrect results. The solution here is to use a frequency map, like a dictionary or an array, to track how many times each character occurs. This ensures that each character is used only as many times as it appears in the input. Another mistake is relying on an inefficient brute force implementation. Generating all permutations of a string, which is factorial in complexity, without pruning invalid solutions like those with adjacent identical characters, wastes computational resources. A better approach is to use backtracking with constraints, allowing you to avoid fully generating invalid permutations. Lastly, many people overlook edge cases, such as when the input is an empty string, contains a single character, or has all identical characters like AA. These can cause errors or even infinite loops. To handle these, you should explicitly check for such cases before diving into the algorithm. For instance, if all characters are identical, you can simply return the input string as the result. Another common pitfall is mismanaging recursion states. When using a recursive approach, it's critical to undo any changes made to the frequency map or character usage after each recursive call. If you forget to reset these states, it can corrupt the algorithm and lead to incorrect results. This is why backtracking is so important. It ensures that each recursive step starts with a clean slate. Additionally, some variations of this problem introduce extra constraints, like requiring a minimum separation of k characters between identical ones. If you overlook these constraints, your solution may fail to meet the problem's requirements. The key here is to carefully read the problem description and adapt your algorithm accordingly. This could involve modifying the frequency map or adjusting the way you validate states during recursion. From an interview perspective, this problem provides a great opportunity to demonstrate several key skills. First, it highlights the importance of pattern recognition. This is a classic constraint-based backtracking problem, and recognizing when to prune the recursion tree, such as avoiding permutations with adjacent duplicates, is crucial for optimizing the solution. Second, communication is key. You should clearly explain the trade-offs between brute force and optimized approaches. For example, you might discuss how a brute force solution has factorial complexity, while an optimized approach like backtracking or greedy methods can reduce unnecessary computations. Third, edge case analysis is something interviewers love to see. Mentioning cases like an empty string, a single character, or all identical characters demonstrates thoroughness. Finally, if time allows, you can compare different approaches like brute force, backtracking, and greedy algorithms and discuss their pros and cons in the context of the problem's input size and constraints. This shows a deep understanding of algorithmic trade-offs. This problem also has ties to several related problems, which can help reinforce your understanding. For example, LeetCode problem 47, Permutations 2, focuses on generating unique permutations when the input contains duplicate characters. It's a natural extension of this problem. On the other hand, LeetCode 46, Permutations, is a simpler version where you generate all permutations without worrying about duplicates. Another interesting connection is LeetCode 31, Next Permutation, which is about finding the lexicographical next arrangement of a permutation. And of course, LeetCode 767, Reorganize String, the problem we're discussing, specifically requires rearranging characters so that no two adjacent characters are the same. Exploring these related problems can provide deeper insight into the techniques and patterns common to permutation-based algorithms. Now, let's explore some alternative approaches and their trade-offs. A greedy approach is one option where you iteratively build the result string by selecting the most frequent character, ensuring it satisfies the problem's constraints. This method is faster than backtracking for large inputs, but it might not work for all variations, especially those requiring all permutations. Backtracking with pruning is another powerful technique. It allows you to generate permutations recursively while skipping invalid states early. This method is highly flexible and naturally handles constraints, but it can be computationally expensive for large inputs. Lastly, there's Heap's algorithm, which provides a systematic way to generate all permutations. It's efficient in terms of memory usage and avoids redundant swaps. However, it doesn't inherently address constraints like avoiding adjacent duplicates, so additional logic would be required. Each of these approaches has its strengths and weaknesses, and the best choice depends on the specific problem requirements and constraints. Great job! We've successfully solved the problem by using a max heap to reorganize the string. Remember, this approach highlights the importance of greedy algorithms and efficient data structures. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!